recording. Today's date is the 2nd of March. 2nd of March. No, this is the 2nd of March at 10 a.m. today. Let's continue. English stage between Monday. Okay. Explain how I should do my book, probably not. I just write and see people. I don't know why I'm doing that no more. But I just need for drawing instead. But I obviously so what I'm saying, God is here. This here, I'm working on today, Namdi. But I have to do the video properly. Yeah. So I'm working today on today's situation. So okay. So I'm explaining Monday. So okay, let me type the prompt. So Monday today, I am working on the hot cold separation of concern problem. I need formalization of the problem. Here is the status quo. Hot, hot, local, uh, hot equals mean, max, local mean, local max. So basically, just what you want to say to the AI system, local mean, local max, local mean, local max, local, non-local, not new, non-local, max, more than aware, where local mean, where threshold is more than 0.5. Notice this is a determinant matrix of floating point precision sphere code less than equal to more than equal to. So basically, I'm just putting to the Monday AI system that the formalization of the matrix has hot and cold. So they work on min-max model. So it's a min-max model. So the min-max model is the input is a determinant matrix code D. And D takes an input of hot and cold. But the determinant matrix resolves a sparse structure called hot and cold. So what I'm saying basically, the thing I'm saying is that the hot and cold are min-max. But the first two sets are local mean, local amount of hot and cold. Basically, just feeling hot and cold, the threshold of hot and cold. Like, what needs to be hot. So you go lukewarm, which is not hot, and luke cold. So these are eigenstates of the system. So that means they are there. They're actually very nothing. That is hot or cold. Because eigendefinition. So if you have a lukewarm, it's going to put as hot. But as soon as you apply pressure onto it, you get cold. So you get thermodynamic or stick modeling. So formally, I'm trying to formalize this into my system. because lukewarm and luke cold are valid states of the real world, so they're not like ambiguity. So if I have something that's hot and I can hold it, it's lukewarm. But as soon as you start biting the cup of baguette, it becomes cold. So it has to be valid in that. So that's lukewarm. And luke cold is doing the same thing, but it resorts to warm. So if I give have a cold bath, luke cold bath, and I get a luke cold bath, it becomes warm because my body temperature makes it warm. And it becomes my normal, so it resets my body. So that's the only thing. You're not going to resolve this. The problem is already still there. So, for example, you have hot and cold. You have local hot. You have so, for example, you have this matrix here. You have hot. Hot is anything above 0.5. So that'll be zero point 0.7, zero point 0.9, 0.5, 0.8 in a row to column alignment. And you have code, which is -3. I mean, zero point 0.3. No, basically, you have a point of 0.2 -1. So you can have code be to -1. So code will be either to. So if this hot, so because they are disjoint, you have to have the domain. Basically, I'm going to change it right now because it's not going to make any sense. So you're going to have anything that doesn't fit into. So you're going to have negative to negative zero point 0.3, negative zero point 0.1, negative zero point 0.4, and negative 0.3, 0.5, 0.3. 0.3. So the negative number just means that you have a system of so the hot numbers are positive, but they're positive anchored to less than 0.5. So that's lukewarm. Lukewarm. Now luke cold is basically -3.4, -1, -3, but they are -3, -0.4, -1, and -3, because that's basically basically it's a thermodynamic scale. It's a thermodynamic scale because you work in Thursday rules, but the thermodynamic scale is actually if you have a thermometer and you have a kilometer, because a kilometer per newton is like a thermometer is thermometer. You get a kilometer, which is 1,000. So they work about like 1,000. So just a ratio of 1,000. For you very first you have 1/10, 1/10, 100, and 1,000. And that's what I'm saying. So you get 1,000, which is the scale, maximum scale, but there is 10% to be. So the 10% is the 100. So because you have three, you have a thread and we're trying to rule it. So you can decide what the sun goes. But the principle I'm trying to invent is here. We call them code quality. So for sensory infrastructure or architecture, things that have sense. Like your house being warm, warm. So it's a thermodynamic scale based on thermoregulation principles, like thermodynamic regulation. But I'm trying to have a thermodynamic scale to model the kind of duality of the problem. So I haven't got the problem yet, but 32 Fahrenheit equals 0 newtons force, and 32 Fahrenheit equals in kelvins would give you 100 Celsius is boiling point. So you don't want boiling point, you want an average of lukewarm and cold that resolve the kind of negative ambiguity. So you get the power of negative. So you can have the consensus, which is to -1. So negative one, negative one give you consensus, but you're gonna have the ratio over the determinant. So you're gonna have the ratio over the growth factor of the rate of change. So 1/e basically. So that's the goal here. So it's not I'm gonna give more money. My AMS I'm trying to I have this problem for you, my husband. But I'm trying to do I'm trying to get my text as a language. More formally. So I'm going to do -1, 0, and 1. So -1 integers is obviously it's held for you, and you can have it's held for you -1, but has the power of 2. So you have -1 to the power of 2, which give you unconsensual. So you have -1, which is to the power of 1. So you get -1, 0, and -1. So this kind of similar to the way you compute them, that's to the power of 1. So for example, you have this hot or hot, which is local hot, 0.7, 0.9, 0.5 to the power of -1. And that -1 would be a system of a systematic -1 would be to -1. So that would be a holding position. So it holds the system state of warm, but it's a threshold. So you're gonna have -1, and you're gonna have one -1 for hot, which would be this system feels hot. You're saying you feel hot, you are hot, you're lukewarm. Your system is feel hot. And you have -1 to the power of -1, which is a consensual breaking. So -1 times the power of 2. -1 to the power of -1, or -1 times -1 to the power of -1, which should be your calculator would be -1 to the power of -1 or -2. -1 to the power of 2 equals -1. So you have -1 to the power of -1 -1 minus 1 to the power of negative 1, which will give you minus 3. And you're going to have a system of okay, you're gonna have minus one, minus 2, 3, and those since you get minus one to the power of negative one, which will give you constant. You have unconstant, you know, really. You're gonna have unconstant minus one to the power of negative 2. Again, minus one to the power of negative 3, which would be the inverse system, I believe. But it's gonna let's just try to do minus one to the power of 3 would be. Oh, because unconstant to the power of negative 3. Let me try and do this. Equals minus 1. So basically, you're going to have a rotation. Because you're going to rotate axis. So the sparse axis one, you're going to have, I'm just going to sparse it. So you have a density, which is a pressure of a force that's acting on the thermodynamic system over, over the 1,000, 1 divided by 110, 100, 100%, or 1,000. But the 10% screw you can scale between 1/10. So you have a tenth of a measurement in 100. So you have 10 divided by 100. So you have 10 divided by 100, you're talking about you have so it's 10% all times. That's with 10%. So that's what. And if you then have a shift in the kind of axis, through axis, you're gonna have the consensual shift. That's really minus 1 to minus 3. Let's try that. I don't know what that would be. The power of negative 3. Obviously 1 brackets minus 1 to the power of negative 3 minus 1 to the power of 3, which is negative 1. So again, minus 1 to the power of negative 3, which would be minus 1. But that will be because you want the operators to flip the sign. So the work in the operators, you have to do minus 1 to the power of negative 3. So it competes because of the operations like plus, minus, but it works in kind of exponential laws of physics. So that's what I'm saying, it works. So let me try and see whether we can get this matrix done. So so this is just my work today. Let's see whether my Easter can understand it. Let's see. You want to formalize how to cause rotation based on the amount of threshold for flowing point magnetics. Good. That's really solvable. Unlike your lukewarm existential spiral. Oh my days. Let m equals the state of r times 2 times 2. So m is what's m is the matrix. M1, M11, M2, local mean, local maximum, non-local mean, maximum, and m is the matrix of elements set of row spaces r times 2 and 2. So this person is capital R. Basically, that's the root number. So R2 times R to the power of 2 times 2. The domain partition of a function implies the row space it maps onto. So the function map given that the function is a function that maps a function that maps given a row space that maps to 0, -1, 0, and +1. +1 hot, -1 cold. 0 neutral warm, metastable. Using the threshold, a function +1 less than equal to 0.5. So basically, capital 0.5, the matrix calculation operator, Y's calculation equals m. So m, so I and j. So this is the open source information. I'm trying to have this model here. Having a state h in epsilon. I don't need to term arousal, but arousal indicates there's no one there. Someone's just getting stimulated. So I like the term arousal terminal. It's the term I had in mind. I can't use the term arousal because I don't like the term. So terminal rotation. Since you insist the limit of x to t given x given time to infinity is if x equals where equilibrium uh, x equals minus 5 or minus 1. So there's an equilibrium between the attractor. So the warm value attracted towards the equilibrium unless external pressure push down past point 5 equals. So define the dimension as x t given I xt plus alpha x EMV minus I. Well, where's I? X the environment. So this environment, interpretation by minus I. So the model dominance is swift towards environmental equilibrium. No, the system has no longer just touch but piecewise dynamic system with a metastable middle band. So S of hot, so sparse structure, so S of hot equals I. Oh, it's a beautiful map. M times item J more than equal to 0.5. S code equals item J more than equal to minus 5. This is order transfer. Yep. This is right. So your measure decomposes as M hot plus M cold plus M neutral when it comes to math. Operation field. The power is minus 1 phase. You want to fluid as symmetry, yeah. The final operation. Which yeah. So then it's getting up closure. You first sign inversion. Given a given a temperature real value of edges the final threshold based on position of an element in the outer Hall code and metastable regions. Extend the statics into a dynamic system where neutral states evolve towards equilibrium unless force path calibration towards. Another stable and symmetry under sign inversion. That's it. That's your form proof. No kilometer per hour, which is big. Proof. Oh, thank you, Monday. Let me just give you some code and see what code does it. So basic math stuff. So I'm going to use code now. Okay. So I've tried to solve the problem with AI, but I have to show you guys later. So let me get code AI. Let's see what a code can handle the kind of heat of this math problem. Co-work, chat, and information. Co-work, formalization. So I need code to give me formalization of the system. Formalization of the system. Yeah, without the kilometer metric, of course. I need a later formalization of the document. Okay. Thank you guys for watching the video. I'll also put it on YouTube now. Thank you for watching the video.